I'm just going to share my screen here and
Yep.
Yeah. Are you guys seeing the screen there?
Yep.
Good deal. Okay, well, welcome everyone to the ARMA monthly technical induced seismicity webinars. I'm Sean Maxwell with Olintiv, and on behalf of the committee, Ahmad Gassami, Jens Lundstern, and Madi Haddad, we welcome you to the webinars. So today we're very pleased to have Mike Brudzinski talk. Mike's going to be talking about seismicity in northern Kansas. Be an interesting webinar, I'm sure. Before we get started with Mike, though, we do have a few announcements, housekeeping things. So I'm going to pass it over to Jens.
Yeah, good morning, everybody. Just like to announce the next two talks. The next one will be the first Friday of November at 10 a.m., so the same time. We're going to have a panel. Right now, there are three participants, and that may increase. Stefan Wiemer from ETH Zurich, Jean Schmidbull, and Ahmad Gassemi will be speaking. And then the following month, there will be the first Friday of that month, the 1st of December, Paul Siegel from Stanford will be presenting. So stay tuned.
Good morning, everyone. Thank you so much for joining another Induced Seismicity webinar. This is Mahdi Haddad from the Bureau of Economic Geology. Before running through this webinar, I would like to highlight a few logistics. So please feel free to share the webinar invite with the interested parties among your colleagues or within your company. We would like to send this notification for the webinars to a larger community of interested people in induced seismicity. And during this webinar, please submit your questions during or after the talk in the chat button at the bottom of the Zoom meeting window. Please send these questions to everyone in order for us to summarize the questions and use the time better at the end of the webinar. And this specific webinar will be recorded after consultation with Mike. And this recording will be posted on our Induced Seismicity Technical Committee YouTube channel. Please refer to the invitation email for the link to this YouTube channel. And you can also subscribe to the channel to receive notifications about the new upload. Without further delay, let's invite Mike to take over the stage. Mike, thank you for presenting.
No worries. Let me put my screen up so that I can share that with everyone. Great. So thanks to the committee for inviting me to present today. I have enjoyed this webinar series quite a bit. Although today I really should say that I'm presenting on behalf of Shannon Fasola, who is my former PhD student and had gone to Kansas for her postdoctoral work to work with Noel Jackson, and primarily to work on slow slip in subduction zones. One of the things that she worked on a little bit with me and really wanted to sort of improve her geodetic toolkit. But then earthquakes were happening not too far away that she was intrigued by, and so pulled back to her prior work on induced seismicity as well. And so really kind of did this as a side project during her postdoc. Did well enough at it that they've kept her on for an extra year. The department was able to hire her for an extra year to continue her work on the induced seismicity. So this is a sum total of the work that she sort of did as a side project, and we'll be exploring some more of that during her additional year. But it is just a one-year position, so folks should know that Shannon is on the job market and happy to talk to you about that if you're looking to hire. So I want to get right into it in terms of the meat of this, right? And that it really will be in many ways an overview of what's been happening in Kansas over the last sort of few decades. So on the left is sort of the older seismicity, the more historical type in Kansas, primarily looking at magnitude 2 and larger. And that in essence, what we see is a limited amount of seismicity, about one earthquake every 2 years. And the seismicity primarily occurred in sort of mapped fault zones in the state. There was a bit of an increase in the 90s and early teens and aughts up in the central Kansas uplift region. In the late 80s, there was a 4 there that was interpreted to be due to wastewater disposal, and actions taken and sort of died away. Then from 2014 onward, we saw a significant increase in the amount of seismicity. The magnitude 3 and larger events grew over 40 times the rate of background. And there's been a lot of focus in Harper and Sumner County through recent papers exploring that region and its relationship to seismicity increases in Oklahoma. So you can see, though, it's not just those regions that had seismicity. So we'll try and explore some of that in this talk. This is a preview of stuff I'll get into later on in the talk, but I wanted to just contextualize that, yeah, it does appear, as was seen in Oklahoma, that wastewater disposal has been injection occurred in large volumes into the Arbuckle, and that's been the sort of primary interpretation of seismicity in southern Kansas, and we'll explore whether or not that's a good interpretation for central and northern as well. So this image is showing the sum total of wastewater disposal since 2000, and it incorporates both Class 1 and Class 2 wells. So about 50 Class 1 wells and about almost 4,000 saltwater disposal wells. And I'll get into a little bit about sort of how that was compiled in just a bit. I did want to walk through sort of some of the state actions that have taken place, the response of the state, and that resulted in the Induced Seismicity State Task Force being formed in the spring of 2014. And that was composed of representatives from the KCC, KGS, and KDHE. The KCC Corporation Commission, they're responsible for regulating Class 2 wells, where the Department of Health and Environment is responsible for the Class 1 wells. In September 2014, the response plan went into effect. It called for an enhanced seismic monitoring, as well as a scoring system that would identify significant earthquakes that could help drive the response for the regulatory agencies. So it factored in magnitudes, recurrence rates, and location of nearby structures, and basically looking at when the score went above a threshold, the agencies for Class 1 and 2 wells would be identified, and the wells within a particular area would need to respond. There was an adjustment to this plan after the November 2014 Milan, Kansas earthquake, nearly a magnitude 5. That led to a revised scoring system where the threshold was lowered after that. So I did want to just highlight some specifics of the regulatory action here. The first regulatory order was March 2015. This is where the KGS helped identify 5 areas in Harper and Sumner counties. You can sort of see the circles in these 2 plots down here, and that's circles, they're weird long sausage oval things. And so those were areas with clusters of earthquakes that were identified, and so area labeled as areas of concern. And so large volume wells within those ellipses did stage reductions, eventually reaching maxes about 8,000 barrels per day. There was also enhanced injection volume monitoring, and we did see a reduction in the earthquake activity right away, but it started to pick back up again in the fall of 2015. And so there was a second regulatory action in August 2016, where it expanded the areas of concern to a much broader part of southern Kansas. There were additional mandated stage reductions of volume going from 25 to 16,000 barrels per day for a set of wells, as well as increased availability of the disposal well data on the KGS website, and also an online disposal volume reporting system. Everything was on paper records prior to 2015. So improvements there to be able to monitor. All right, so that's sort of the summary of regulatory action in the state. And so I want to just kind of cover that from the beginning. Now I'm going to shift over to talking about the prior research in the area. So I'm going to start with the Choi et al. Paper, a nice summary of the Milan earthquake. That's the largest recorded earthquake in Kansas to date. The causative fault is inferred to be an unmapped basement fault. You can sort of see a zoomed in area of the fault zone here, and that it fits within the sort of Nemaha fault zone as you look more broadly northward into the state. The earthquake has the characteristics associated with other earthquakes that have been induced by fluid injection, and part of that comes from the timing and spatial relationship of wells in the area. So this plot over here to the right shows disposal well activity. There are a couple of wells that are sort of nearby that are less than 10 kilometers, about 5 kilometers away, that have an increase a few months before the foreshock and the main shock. And then we have increases at further distance, about 15 kilometers away over here, relative to the seismicity, where those increase in disposal pretty close to when the foreshock took place a few months before the main shock. So a relatively straightforward story about disposal being related to those events, although the volumes here are smaller than others further to the south and west in the county and over into the neighboring county. So that leads into the Rubenstein work in 2018, where they used a local network to establish better locations and better detect events. They were able to show that earthquakes were mainly occurring in the shallow crystalline basement below the wastewater injection horizon in the Arbuckle. They also were able to identify that the seismicity does correlate in space and time with injection. This is just sort of a summary plot that sort of shows how the earthquake rates come up as those injection volumes come up, and just pretty clearly demonstrated that the earthquake rate change it's statistically improbable to be natural, right? That this is being forced by the disposal. They also identified that there wasn't hydraulic fracture or oil production in the area that correlated in space and time with the earthquake. So again, a pretty clear story that disposal is having an influence on it. Although, again, in this plot here that sort of looks at the total injected volume over that sort of 4 or 5 year span, right? You see some of the seismicity, particularly up here near the Milan events, that's further away from the highest amounts of injection that are further to the southwest area of the study area. So again, a little bit of variation in terms of behavior. The Cochran et al. Paper sort of explored this in a little bit more detail. They used the Rubenstein et al. Catalog and then performed template matching on it to enhance it, and then tried to explore temporal patterns of the seismicity. You can see sort of magnitudes over time plots here that show much more clustering for some and much more consistent patterns for others. They used a coefficient of variation of the inter-event times as a way to kind of characterize that pattern, where the high COV values were for the very clustered sequences. The low COV values near 1 are more for the consistent pattern of seismicity over time. And so they inferred that because the sort of low COV values were happening closest to the high rate disposal, that would be from that increased pore fluid pressure and a sustainable and high level, that was driving these sort of long duration sequences. Whereas the seismicity that's further away from the high rate disposal tended to have more of these earthquake interactions, because it's not just the disposal that's driving the seismicity. While it's playing a role in sparking it, the earthquakes themselves can interact enough to maintain that over time. All right. I also want to touch on some work that started to look at some pressures that were measured by the Class 1 wells. So this is the Ansari et al. 2019 and the Ansari and Bigoli paper 2021, where they looked at fall-off test pressures, static fluid levels, and the injected volumes. And they found that the Arbuckle pressures and fluid levels were rising recently at faster rates, and that they were associated with the increased wastewater disposal. So it indicated that pressure diffusion can reach to distances upwards of 25 kilometers from the injection point, and that the fluid pressure diffusion is connected to the static fluid level rises that were being measured. Their study suggested that the Arbuckle has some finite storage capacity, and that we're basically filling it up. The second of the two papers there also explored more of the pressure rate and found that to be more of a dominant control on the seismicity, right? So this plot over here to the right just showing that the rate on the bottom and the total pressure on the top, right? That you can sort of maintain a sort of high pressure level, even though the pressure rate may be relatively low. So this is a little different than some of the other studies, particularly in Oklahoma, that suggest the pressure rate would be more of a driver. Consistent with some of the work in Oklahoma that would suggest pressure rate being a consistent driver. All right, so the last sort of review paper I want to sort of touch on here is the Zai et al. Paper that looked at more hydromechanical and seismicity rate modeling to assess the effects of injection from northern Oklahoma on southern Kansas and vice versa, basically looking at how things on either side of the border may influence seismicity on the other side. And so they identified that the injection in Oklahoma was amplifying the total Coulomb stress change by about 50%, and the seismicity rate by a factor of 3 in Kansas, right? So for example, over here on the left, you can see this is just incorporating the Kansas wells. This is the Kansas wells plus Oklahoma, and you can see that the difference is sizable here, right? And so it's having a significant influence on the likelihood of seismicity. That's the plot over here, just showing how we're shifting from the dashed line to the solid line in terms of the likelihood of seismicity of any given size based on that change in the Coulomb stress. Oh, sorry, just that last point here, just to kind of underscore, right, that basically they concluded that induced seismicity is not just a local problem, right, that it has to do with this far-reaching effects of pressure diffusion. So some indications that fluid pressures are migrating in the Arbuckle depending on the rates and sizes, and that's something to be mindful of. All right, so that's kind of the backdrop then for our work, right? So studies that I just reviewed there are primarily focusing on seismicity in this area here. But you can see that, by the time sort of 2017 arrives, much like in Oklahoma, the seismicity rate starts to tail off a bit, right? So the gray line here is showing seismicity south of that purple line, and that, the rates are slowing in that area. Whereas seismicity to the north of that purple line are really just picking up in 2016 and really taking off in the last few years. So a bit of a different behavior of the seismicity in the northern part of the state. So that sort of sparked Shannon's interest on this, and why we've been focusing on it for the last few years. So I think it's fair to say the earthquakes are saying we're not in southern Kansas anymore. And so in addition to those rate increases in northern Kansas, we were then also seeing large magnitude events, right? That 9 out of the 10 magnitude 4 and larger events since 2019 have occurred north of that sort of Harper or Sumner County area that had been the focus of prior studies. So you can see, the disposal here in this plot also is not just focused in southern Oklahoma, that there is plenty of disposal in central and upwards of northern Kansas. So, for us, there's a couple of study questions that drove this work, which is, basically, what is the nature of these earthquakes? Can the regions that we're looking at here in the central and northern parts also be tied to wastewater injection? And if so, what is the relative role of local versus regional wells? So those are kind of the guiding questions. And so hold on to Toto, here we go. This is the approach that we took. The first would be really just kind of trying to collect and refine our operational records, right? So Shannon has spent quite a bit of time on this part of the project, trying to collate all of the wastewater disposal well data, right? We have class 1 and class 2 wells. The class 1 wells, the annuals came from the Ansari work, and then also was able to obtain monthly records from the KDHE, and then eventually from the KGS website for the most recent set of years. The class 1 wells also have bottom hole pressures. So the annual sort of bottom hole pressures came from Ansari's work up through 2017, and then via request from KDHE since then. And then for the class 2 saltwater disposal wells, the monthlies are all now available from the KGS website, but it takes an extensive effort to clean that data set and identify the wells that are injecting into the Arbuckle or lower, and discriminating those from shallower horizons. So a lot of time spent on that. Also collated all the data from UR wells, enhanced recovery wells. And so that data is available from the KGS website as well as the production well data, but have to do that monthly by lease to be able to sort of get that. And then collected the hydraulic fracture information from Frac Focus. So that was our operational sort of data. And then in terms of the seismicity data, we applied template matching to enhance the detected seismicity. There is a limited station density in Kansas, but we were able to retrieve continuous data from a variety of KGS stations to be able to help analyze events in different parts of the state. We did primarily apply single station correlation, and that's because of the limited station density. So we had to work a little bit harder on manually reviewing the matches to maximize the detected events and discard repetitive noise. So we generally used relatively high correlation coefficients for our cutoff, and for now have kept it sort of standard across all the different regions. We use the KGS and Comcat catalogs for templates. And then the results I'm going to show you today are primarily focused on regions with the MN4 larger events, right? So these 4 sort of boxes here are the 4 regions that had the larger events. So that's where we're going to focus the review of in this study. All right, so I did want to summarize the industrial operations first, just because it's a pretty straightforward story, right? So again, I've got the sort of 4 regions that we'll be focusing on, highlighted in red, as well as the 3 down here that were kind of the primary focus of prior work. And you can see, over here in the top right is our wastewater disposal that you've seen a couple of times now, that plot. And I put it up here just for some comparison with these others, right? So if you look at the produced oil, the volumes are much smaller than the wastewater disposal volumes. So pretty hard to argue that would trade off with the disposal. The hydraulic fracture wells also do not spatially correlate with the seismicity that we studied. There's only a little bit, even that sort of within the 4 regions that I'll be looking at here in Reno County, but the seismicity in that area is off to the eastern side of the county, so not even spatially correlated in that case. There is significant gas production throughout the southern part of and a bit into the central part of the state, but really didn't, again, correlate spatially with the areas that we're focused on. And then the EOR over here to the right, there is some overlap with some of the areas that we looked at, but it does tend to trade off with the production, and it's smaller than the wastewater disposal volume. So we thought those things alone probably would suggest it's not as important, but also the targets are typically quite a bit shallower than the Arbuckle. So again, probably would have less influence at the depths that we're concerned about for seismicity. I will note that just all of these 4 plots are basically showing the results for all intervals, not just the Arbuckle. There is some production that comes from the Arbuckle, but plenty of it that comes shallower than the Arbuckle as well. And I haven't separated it out here. I'm just trying to give you a kind of an overview picture of it. All right, so now I'm going to head into the seismicity in each of these 4 regions. So over here, I've got the area that I'm focused on, that we refer to it as the Hutchinson region. It's part of Reno County. Hutchinson is the city that's nearby where the earthquakes have been occurring. And so up until 2016, there were really no recorded earthquakes in this area. Then after 2016, the max magnitudes were about a magnitude 3 on average until 2019, when things sprang up into the 4 size, and there were 3 magnitude 4 plus events, a 4.6 and a 4.4 in August of 2019, and then a 4.8 in January 2020. And that's the 3rd largest earthquake that's been recorded in Kansas. You can see the overall pattern of magnitude over time here with the templates in black and the matches in gray. And then we've zeroed in on the magnitude 4 portion of the time series here, just so you can see, yeah, there are some patterns of main shock, aftershock, like sort of decay to them, and a little bit of Bass law, but you can see, not so great here when you've got a 4.6 and a 4.4. And so plenty of swarminess to these sequences as well. A relatively low p-value for this region. And also when we looked at the inter-event times, we found that the average coefficient of variation is about a 3 in this region. So relatively clustered, not down near 1, like one might expect if this is being, primarily driven by that sort of substantial pressure nearby, like we'd seen in southern Kansas. So, I did also just want to note that this region had pretty clear strike slip focal mechanisms. The trend of the seismicity would suggest that it's a sort of a northeast southwest oriented fault, and so the strike slip mechanism would probably be right lateral in this case. All right, next I'm going to look at some prior work that's been done to try and understand how the disposal might drive this, and it's primarily based on a nearby class 1 well that has downhole pressure measurements for it. So this prior work primarily comes from the Peter work, where they evaluated the contributions of local and regional disposal and how it relates to the Hutchinson earthquakes. Hutchinson earthquakes are primarily targeted in the 2020, less so in the 2018 paper. But basically, they're using the formation pressure, disposal volumes, and the measured seismicity to try and put together a story for this. As noted on the prior slide, there are a few nearby disposal wells that have high rate injection. They estimated from the 2020 study that the locally elevated pressures there may be about 1 megapascal. But when they looked in the earlier paper 2018 in the Harper Summer areas, that in essence, you couldn't generate the pressures that were being observed downhole with just the local wells within 20 kilometers. So again, a limited response from the local wells. And instead, they found that the temporal pressure trends and northward migration of the earthquakes suggested more pressure diffusion from the high rate wells. So even up here in Hutchinson, they're arguing the wells down here are even 90 kilometers away to the south were influencing the pressure in the Hutchinson well, maybe on the order of 0.2 megapascals. So they're making the argument that it's a combined pressure effect from the local and the distal wells, and so that would combine together to give the sort of pressure change needed to generate seismicity. All right, so we looked at this as well, exploring the cumulative volume that's been injected both locally and regionally. And then, given that the class 1 well that's measuring the pressure is right nearby, we could sort of look at, how did that compare to the seismicity? We found that the pressure gradient being measured in this well does not correlate well with the local wells. This is sort of consistent with the prior work that in essence, you get this jump in the disposal back in about 2006-07, and that the pressure gradient increase is not until the teens, 2014-15 or so. That correlates better with what we see in terms of wastewater disposal wells when we expand it out to 40 kilometers, right? So the solid blue line here is for wells that are within 25 kilometers. The dashed dotted blue line here is for 40 kilometers away. And that seems to match better with the red curve, which is the pressure gradient being measured at that class 1 well. I also have a plot over here that shows the seismicity in terms of magnitude over time with the absolute pressure. And so it was intriguing to us that we saw that, yeah, the pressure gradient doesn't correlate very well with the seismicity. It's really more the sort of max pressure that seems to correlate. So, it feels for us that our conclusions are a little bit different than prior work, and that it seems more likely due to increased pressure as opposed to pressure rate. And from the regional wells that are only up to about 40 kilometers away, that you wouldn't need to go all the way out to 90 kilometers away to be able to match the pressure gradient. All right, so that was the Hutchinson region, Reno County area. I'm moving on to the Salina area, again, Saline County and the nearby Salina City. So Salina, sorry, I got to get that right. This region did not have recorded earthquakes until January 2010. And there's a small swarm that took place at the beginning of 2010, and then a real quiet period where there isn't either recorded catalog seismicity or template match seismicity until late 2014. And we start to see more of a rate increase in 2016. That continues to build over time, both in terms of rate as well as the maximum magnitude, and reaching the sort of larger size events in 2021, where we have three 4 and larger events, 2 4.2s and a 4, all of which are in a few days of one another in December of 2021. This is a zoomed in view of that portion of the time series, so you can see the 4 size events here. Again, little hints of an Omori decay, but again, clearly a swarm-like pattern here based on similar max magnitudes and a similar rate overall over time. Again, another low B value in this region, and the inner event times, we see the COV here is a little bit larger, about a 4.2 if you average together sort of the seismicity over this region by looking at it both based on templates as well as individual regions. So again, we suggest that the events here are a little bit more clustered further from the source. So even though there is some disposal nearby, again, we have some seismicity that is not near the disposal. So perhaps maybe contributing to the larger COVs. Again, the focal mechanisms in this area show strike slip mechanisms, although a little harder to deduce the fault patterns in this area. This region here looks to have more of a east-west sort of trajectory, so perhaps more of a left lateral fault in that system. All right, so I wanted to compare with the disposal in this area as well. I mentioned, when looking at the overview map, right, that we have some larger disposal that's nearby, but generally it's further from the high rate wells that are further to the south, right? This is more of a moderate to low rate when we're looking at volumes nearby. You can sort of see that here on this plot in terms of the annual volumes when you're looking at within 10 kilometers of where the fours took place. The annual volumes are on the sort of 2 million barrels, whereas if you look out to 45 kilometers, you're up in the hundreds of millions over the annual rates. So again, if you look at the northern seismicity, we're even further away. Those measurements there were really sort of within the distance of where the magnitude 4 was. So the other thing we noticed is that, if you look at the monthly volumes, maybe there's a little bit of a correlation in that when we have some spikes in the monthly volumes, there are some increases in seismicity, but that's a pretty weak correlation at best, and certainly with a lag in it of at least 6 months. So again, some more detailed pressure modeling might be able to sort of deduce how much of an influence there is between sort of local versus regional. But generally, it appears, at least using the pressure from a downhole well that's some distance away, about 45 kilometers away, it does appear that the sort of regional wells are driving the pressure gradient more than the local wells are. And again, this is another case where the increases in seismicity followed the increase in pressure gradient. So more consistent with when there was higher pressure as opposed to when there was higher pressure rate. All right, so I'm going to move to the next region, the Central Kansas Uplift region. So that's up here in this area now. So moving a little bit more to the north and the west. And this is certainly of the 4 regions we're going to look at, the region that has the highest cumulative rate of injection. You can see in this plot here, much deeper blues now, again, using the same scale as we have in the prior plots, and it's spread across this region. So this region did have a 4.8 event. That is the second largest to the Milan event that took place in this region. That's what's in this gold box here. And this is the overall rate of seismicity throughout the whole region. And you can see, there is seismicity back in the early 2010s, and sort of certainly when you look at the sort of historic seismicity, it goes back further in this region. So we don't think this is the beginning of seismicity, but it's sort of sporadic until about 2016, where it really picks up, and then the magnitude 4 happens in 2019. And so when you zoom in on the pattern here, it's certainly buried within a swarm where the magnitude 4.8 has about 2 months of prior activity and about 7 months of waning activity at a relatively constant rate before kind of declining after that. And so this, mimics other seismicity in this region. Each of these sort of clusters of seismicity has pretty swarm-like behavior to it, relatively low B-value, as well as the inter-event time COVs are, again, sort of relatively high, 3.8 for this region, suggesting some form of clustering. Again, we see a little bit of clustering going on, but still not showing a consistent pattern over time, suggesting that despite the fact that there is disposal right nearby any winner of the seismicity, that perhaps is being driven more regionally, not just by the local well. The other thing to mention here about the seismicity is that, again, they're primarily strikes up focal mechanisms, but we are seeing a little bit of rotation here. There is some obliqueness to some of these events that push a little bit more into the normal faulting terrain. All right, so I did also then want to touch on the disposal that's going on in this area. As I mentioned earlier, right, there's plenty of disposal going on in this area, and that you can kind of summarize that by 80% of the seismicity is occurring within 10 kilometers of a large, high rate waste disposal well, at least 50,000 barrels per month. That said, trying to sort of correlate it to individual wells is tough. If you look at just basically all of the disposal in this whole sort of area, anything within 10 kilometers of the study area, and you look at the annual, you get a decent trend that when we get sort of a peak in the volume, that's when the seismicity really starts to pick up. And even if you just sort of narrow down to within 10 kilometers of the 4.8 event that's in this cold box, again, you do see that the seismicity picks up when you're at that sort of peak in the annual volume. So there is some relationship there. But when you look at the sort of monthly patterns, either regionally on the whole box or within sort of a narrow zone around the cold box, we don't see these sort of stronger correlations between monthly rates and increases in seismicity. Perhaps there's a little bit of a trend here where there's an increase and then the seismicity occurs at the top end of that. But we have other timeframes where that did not occur. So again, not well correlated, associated with the monthly volumes. So again, I think we're quite a distance away from any class 1 wells here that we could use for downhole pressure measurements. So we're really in need of more downhole pressure measurements to be able to better understand what's going on here. And some commensurate fluid pressure modeling would help to try and unravel, what's the relationship between sort of individual wells versus the collective set of wells. But there seem to be some indications that it's a collective set of wells that matters more here than the individual wells. I did also want to do some comparison then between what we're seeing here in the central Kansas uplift region here, so shown here, with that region down near the border, the Harper, Sumner County areas. So in this comparison, we're trying to do similar size areas, and we're looking at all the wastewater disposal volumes within 10 kilometers. So again, I'm not using all of the disposal volumes down into Oklahoma here, just the stuff that's nearby within 10 kilometers. And so we find twice as much of the total volume injected into the central Kansas uplift than what we saw injected into the Harper, Sumner County areas. But they're much more constant in the central Kansas uplift than they were in the Harper, Sumner County areas, right? So I should probably explain this plot, right? The blue lines, the solid one is the Harper, Sumner County volumes, and then the dash dotted lines, that's for the central Kansas uplift, and the scale bar shown over here for the injected volumes, right? And you could just see that because it's been more constant, that's how you can get the higher total volumes, right? If you go back to 2000, there's high rate since then, whereas there's more of an anomaly in the teens for Harper, Sumner County. And so, it appears that the seismicity responded, right? That when there was that sort of dramatic rise in the disposal in Harper, Sumner County, the earthquakes correspondingly rose. Whereas the central Kansas uplift seismicity is at a much lower rate, and does not have that sort of big peak either in the seismicity or in the disposal. All right, the last region I wanted to look at is perhaps the most interesting because it's occurring in an area that does not have disposal wells nearby. Right, you can see on this map, right, the lack of disposal volume in this area. There's also been very little historical seismicity in this area. There is a little bit of a fault area to the southeast of this region, and a little bit, a pair of earthquakes that were observed historically in this region. And then if you look both at the templates and then as the matches, a few earthquakes before 2016, with a small swarm in early 2013 and an even smaller one in 2011. But since 2016, there's been a rapid increase in the magnitude 3 and larger size events, and yet a similar sort of pattern in the frequency magnitude distribution, a low p-value 0.86. This is though where we get the highest coefficient of variation for the interrun times, and we're up upwards of a 6 in this region. So this is sort of the most clustered, and perhaps that's commensurate with it being the furthest from the source area. The other thing to point out is that this region, the focal mechanisms are distinctly normal faulting in this region. So whether or not it's because regionally they're different, or because perhaps the relationship to disposal is different in this region, intriguing as to what might be generating the different focal mechanisms there. When I noted the COV, I also wanted to note just that we have some plots down here to the bottom, just sort of showing when the magnitude 4 size events happen in this region. And you can see, again, sporadic nature of the seismicity. Even when you zoom in on what appears to be sort of clusters of seismicity, they're sporadic in terms of their behavior. All right, so looking at the disposal in this region, right, I've expanded the sort of plot to be able to show this is the Jewell County seismicity. I think you have to go all the way back over to the central Kansas uplift region to get the disposal that could potentially be driving this seismicity. So there basically aren't any wells within 50 kilometers. And there's no enhanced oil recovery or hydraulic fracturing in this area or production right nearby the Jewell County seismicity that could be implicated. So it does appear to be this sort of distant disposal. I did want to note that the first region of seismicity, we call it region 1 over here to the southwest, is the first seismicity to activate. in 2016, but otherwise there isn't really a spatial pattern in that it kind of migrates across this region. It kind of picks up in different regions at different times. Those two wells that are closest to it, 50 kilometers away, have generally small rates, but they do correlate with the timing of seismicity. Right over here at the bottom, these are the annual sort of volumes for those two wells and the timing that correlates with when the seismicity takes off. However, as you head out to larger distances, the volume increases quite a bit as you get past 60 kilometers. It just doesn't correlate as well in time with the seismicity. I mean, it's probably playing a role, but perhaps not the sort of critical triggering factor. That said, even at 50 kilometers distances, those are commensurate with what the Zhai paper had found in terms of distances by which southern Kansas seismicity was potentially being driven in terms of Coulomb fault stress, Coulomb frictional stress, sorry, for wells based in Oklahoma. So again, despite these distances being quite large, they're not out of the realm of possibility given what we've seen from some prior work. So, again, certainly didn't want to rule it out. And I think it reminded us quite a bit of what's been seen in West Texas. If you look at the Delaware Basin area out in Culberson County, may see some similarities there. So let me explain that relationship. So this is primarily coming from the Skomel et al. Paper that did a similar investigation of geoseismicity in the Delaware Basin, looking at template match seismicity and detailed operational records. And they identified that the seismicity in Reeves County was primarily being driven due to nearby wastewater disposal wells, sort of situated within 10 kilometers. And that as you go along the edges, you could see some cases where hydraulic fracturing was driving the seismicity. But this area up here in Culberson County was primarily being driven by far field disposal wells, generally greater than 25 kilometers away. And noted even in that paper about the sort of different temporal patterns of that seismicity, right? That the Reeves seismicity had more of this sort of continuous pattern with low coefficient of variation, whereas the seismicity in the far field driven region had more episodic and clustered seismicity. And that's certainly the kind of pattern that we see in the Jewell County area. So again, just noting these similarities between what's been seen in Culberson County versus what's being seen in Jewell County, given that they're both sort of far field driven seismicity, it appears. Again, should note that the max magnitudes in Jewell County are still in the sort of 4 range, not in the 5 like we've seen in Culberson County, but certainly gives me some pause. All right, I just wanted to sort of wrap up here with a summary of the study regions. I know it was kind of a quick tour of each of these different regions, so wanted to kind of lay it out in a summary table so that you might be able to sort of get your bearings in terms of the overall patterns, right? So again, part of the reason we chose each of these 4 regions is that they had some magnitude 4 seismicity to them. Each have at least 2 magnitude 4 or larger events. And then I also wanted to highlight that the number of magnitude 3 and larger events, right? That we have nearly 50 in Jewell County, but less than 20 in Hutchinson. In terms of the timing, the first detected seismicity for Central Kansas uplift that goes back even before sort of our study time frame. The Salina and Jewell County regions are sort of in the early teens, whereas Hutchinson was later, really sort of picking up in 2016. But really for each of these regions, we're seeing the time of increased seismicity is sort of over a few year time span between 2014 and 2016, with primarily things end of 2015 and towards the middle and end of 2016. I did want to note that our template matching was fairly conservative, and so we're not seeing kind of the full order or magnitude increase in the seismicity. So something for some future work potentially. Also looking at the p-values, again, generally low across the board for these regions, and that our coefficient of variations were all in our event times were all relatively high, suggesting clustered activity, and that the highest was seen in sort of the more distally driven region in Jewell County. I tried to summarize sort of the patterns of disposal relative to the seismicity. It's a little tricky in a table form here, but basically looking at how many sort of wells at the 50,000 barrel per month, 100,000 barrel per month, or 300,000 barrel per month in the 3 consecutive sort of parentheses numbers here, and then showing it for 10 kilometers and 40 kilometers, right? So the Central Kansas uplift that has plenty of 50 and 100 at the 10 kilometer, a few for Hutchinson, but you really can see more consistent patterns when you're out beyond 40 kilometers. And so, each of these three regions, I think we would say seems to have some influence from the regional less than 40 kilometer disposal wells in those regions. However, for Jewell County, you would need to go further than that the high rate wells really are out in the 50 to 100 kilometer distances out there. So yeah, certainly some differences for Jewell County relative to the others, but it does appear pretty consistent that we're seeing the influences of regional disposal wells on the seismicity here, suggesting significant far field effects. All right, so I wanted to wrap up with a conclusion slide, just kind of summarize what we found in this work. Seismicity rate has slowed in southern Kansas, like it has in Oklahoma, since sort of 2016 or so. But over that same time frame, we've seen increases in seismicity in central and northern Kansas that were a bit puzzling. And in fact, 9 of the 10 magnitude 4 and larger events since 2019 were in central and northern Kansas. Causing some alarm, I think, for those of us that work on induced seismicity. Seismicity does show signs of being driven by wastewater disposal, generally swarmy, low B values, but it does have these clustered inter-event times that suggest there are strong influences of earthquake interactions, but primarily consistent with being tipped over by the disposal. We did look at other potential industrial drivers of seismicity like hydraulic fracturing, enhanced oil recovery, and production, but they do not correlate in space and time with the seismicity. Again, really pointing back towards the wastewater disposal. We did find a few regions that have wastewater disposal within 10 kilometers of the seismicity, but the timing does not appear to be well correlated in those cases. It does appear more so that we have regions where there's high rate disposal wells at 40 kilometers or less, within 40 kilometers, and that those tend to correlate well in time with both the seismicity and the downhole pressure records when they're available. We do find a few regions, though, that have seismicity that occurs out to 50 kilometers from the disposal wells, and again, providing some pretty strong evidence for the far field fluid diffusion influence on the seismicity, right? So again, I think just trying to sort of communicate the message here that, again, we can't just sort of be exploring the effect of wells that are nearby, that getting out to significantly larger distances is pretty important, and trying to wrap our brains around this problem and how we respond to it. All right, I'm going to go ahead and stop there and open up for questions. Appreciate your time and attention. And again, happy that I was able to give this talk today, but really on Shannon's behalf. So certainly want to applaud her on pulling all this work together.
Great. Well, thanks, Mike. A lot of really interesting observations and some questions on the chat that we can go through. But just before we do that, maybe could you just talk a little bit about the mechanism? Obviously, these are pretty long distances, and in your conclusion, you talked about pressure diffusion. Does that make sense in terms of sort of perm? And the obvious question, what about pore elasticity?
Sure. Yeah, I think I would say my take on this is influenced by work in West Texas recently that suggests relatively high diffusivities in the sort of Arbuckle comp, and so that I'm making some inferences, like has been made in Oklahoma as well. Some of the pressure modeling there suggests relatively high diffusivities in the Arbuckle that would suggest that, yeah, it's primarily pressure diffusion that's enabling changes in the pore fluid pressure of the fault zones at these distances. That said, I think, again, there's some good work that has suggested if you've got compartmentalization of the fluid injection, that could potentially drive the pore elastic stresses pretty high. But I think in this case, given that we're injecting into the Arbuckle that's been shown to have pretty high diffusivities, I would lean more towards the high pressure, high pore fluid pressure diffusion being the primary driver of the seismicity. Again, a nuance to this, right, is that the earthquakes are occurring down in the basement, right? And so the communication between the Arbuckle and the basement is still a component of this that I think we all would agree needs a little bit of additional work to try and sort of suss that out. But I think, yeah, the idea is that the Arbuckle can allow for the pore pressure to communicate at long distances and then can seep into the basement once it's there.
Thanks for that. So why don't we go through the chat window, and there's maybe a couple questions there that we can kind of expand upon. But yeah, Tom Tomastic is asking a couple. Maybe ask the second one first. Were some of the wells directly into basement, and if so, do you know that they've been plugged back?
So I know the first half of that is yes, some were deeper in the Arbuckle and into the basement, but whether they've been plugged back, I don't know the answer to that question. Shannon might know that because she's dug into a little bit deeper on the depths and how they might have changed over time. I see, Shannon, you were able to join us here at the end.
Yes,
did you want to?
Thank you.
No worries. Did you want to weigh in on that one?
So yeah, there are some deep wells in the basement. So I did extensively trying to identify which ones were in the Arbuckle versus, I guess, basically just Arbuckle and below. So I was looking at tops of KGS file of tops of the Arbuckle and trying to compare the well depth to those, but trying to piece out the interval they're injecting after plug back was difficult because in their KGS's injection database, they just list the well when it was drilled. So they don't necessarily list the plug back depth. So it's kind of hard to distinguish to what depth they're plugged back. I think at least I saw a few wells that were plugged back into even shallower than the Arbuckle. So for those, I kind of left out and kind of just kept the wells that were for sure, at least I was confident that were towards the deeper end of Arbuckle and below. But again, that's a tough thing to parse out of the specifics, given the data that's available.
And I'm glad you can join us after my presenting your material for you. So, and on that note, Jason Ellison's asking if the slides would be available. The recording will be available, but Mike, Shannon, I guess it's up to you guys.
Yeah, I would say, I think we were going to be comfortable with that. You may have noted on some of the slides there that we've got a FASOLA in prep. It's basically ready to submit. We really just wanted to showcase the work today to get a little bit of feedback before clicking submit on that. So I think we'd be comfortable with sharing the slides, considering we're going to be submitting the paper here as well.
Soon, yep.
Great. And then Tom had another question coming. Actually, the first question he asked, and have you looked at pressure fall-off tests? And do you know, is this linear or radial flow?
I haven't looked at the exact fall-off test. So those pressure measurements are from fall-off tests. So the original pressure measurements are from Esmail's and Sari's work, where they compiled the pressures based on the fall-off test. And then I gathered the recent years directly from the KDHE. So those pressures are based on the bottom hole pressure fall-off test.
Yeah, Shannon, I could see that Tom's asking a bit about whether there was indications in those tests for whether or not there was more asymmetric flow or more symmetric radial flow. And I don't recall seeing that in the test reports. So Tom, it's a good question. I think we should go back and dig just to make sure there isn't a little bit of additional information there. I'll admit I inferred that they had seen radial flow, but I'm realizing now that's an inference. I don't recall seeing that.
See, I don't have the actual test. It's just I have a text file of the pressures.
Yeah.
Great. So maybe just moving on, Jawad Khan's asking a question about just in general approximate disposal capacities, injection rates, and depths. No doubt there's a range, but
yeah, I was gonna say I could probably flip up slides again to sort of showcase this a little bit, right? But it varied across the region, right? Some wells were well in excess of 300,000 barrels per month, while you've got others that particularly in southern Kansas, when they were taking regulatory action, that were being restricted to rates less than that, and certainly plenty in the central and northern Kansas at lower rates. So again, we had some pretty good size wells. Shannon, I don't know if you've got a sort of max size for some of those class 1 wells that really sort of pumped at the highest rates.
When I remember, it's about one of them reaches about 700,000. And that's
per month.
average per month for the last 5 or so years.
Yeah, and in terms of the disposal depths, again, we really focused on the Arbuckle wells when doing the reporting for the study. Again, just given the likelihood that those wells are going to be more closely interacting with the basement faults. So there is disposal going on at other depths, but we've focused on the Arbuckle in the study that we showed today.
So in the central Kansas uplift region, the next largest interval that they were injecting to was the Cedar Hills sandstone, but those volumes were far less than what they were injecting into the Arbuckle.
Great. And then Jeff Dunn's got a couple questions related to pressure. So the first one, are you seeing any hints of sort of a pressure threshold for the onset of the seismicity similar to Rangeley?
Yeah, I think Shannon and I would say yes. We feel that appears to be a better explanation based on the limited pressure measurements we have and the trying to compile the disposal volumes. It does appear that the seismicity turns on once you're at sort of a max pressure level, as opposed to the pressure rate, right? That we don't see as much of an influence of the pressure rate on the seismicity as we saw in terms of the absolute pressure. So yes, it does appear to be a bit more driven in that direction than the pressure rate. Again, Shannon and I have talked a fair amount about this, that some of these areas have had disposal going on for quite some time, right? And so it does appear that perhaps at some point they reach a level that's just high enough to be able to get these faults to start to activate. So it does appear to be a little bit more consistent with that kind of Rangeley way to think about it.
So I guess just hitting on kind of that pressure change aspect, I think Jeff's asking near well pressures versus far field kind of pressures. Any comments there? Just commenting that the smoother near well.
Yeah, right. And I think that's, in part because we tended to focus on the annual volumes as opposed to the sort of monthly volumes. I think you're right that sort of variability shows up quite a bit more, I think, in the monthly volumes than in the annual volumes. And so, again, when we're showing that variability between sort of near, within 10 kilometers and 45 kilometers, we tend to get a little bit smoother pattern for the 45 kilometers just because we're looking at the annual volumes. I think if you were to do that on the monthly volumes, you'd see quite a bit more variability. We've steered away from those plots because it's hard to pull anything out of them. We really only looked at the monthlies when you've got nearby wells to be able to explore. It's a good point, though. Again, something that I think we should probably take a little bit closer look at is, is there some kind of regional homogeneity that's leading to that?
So another thing I can add is that the reason kind of we focused more on the annuals is that we only have good monthlies back to 2015. And so that relates back to the KCC requiring online reporting in 2015. So prior to that, it was all paper records. And so there's inconsistencies in the monthlies prior to 2015. As in their file, they'll list the monthlies, but then the total of those monthlies won't equal the reported annual. And so it's just based on reporting what was required before 2015. So that's why we look at annual, so that we could see a longer time history going farther back.
Great. Then there's a few other questions. I don't think we're gonna have time within the hour to get to them all, but like Shannon, if you've got a few extra minutes to stick around, maybe we could have more of kind of a informal sort of Q&A afterwards. Maybe just approaching the end of the hour, we can go ahead and kind of wrap up the formal part of the presentation. And I guess, first of all, just on behalf of ARMA, thanks, Mike and Shannon, even though Shannon was kind of silent in the presentation. But, we thank you for the hard work and for Mike doing a great job translating. Excellent work, excellent observations, really kind of thought-provoking. So thank you very much.
Happy to do it. Thanks for the attendance.
Yes.
And just before people jump off, just a quick reminder. The next webinar is going to actually be a discussion panel on geothermal induced seismicity. We're targeting November 3rd at 10 a.m. So as always, watch the invites coming from Madi, and we're excited for the panel discussion on important topic, and more to come on that. So we'll see, hope to see everyone next month. So Mike, Shannon, coming back to the pressure, I guess I was gonna ask about, you talked a lot about pressure gradients versus the absolute pressures. Could you just maybe talk a little bit about the conceptual model around the pressure gradient as causation, as the idea that if you're injecting constant rate and you're seeing those pressures sort of take off, that would be the flag of just overpressuring the system, or what's the causality in mind with the pressure gradient model?
Yeah, I mean, I think the sort of prior work has sort of suggested that the pressure gradient is likely going to have the biggest influence on the sort of forcing stress, you know, in essence, to get seismicity to activate. It would appear that, you know, from the hydromechanical models that your pressure gradient is going to be sort of the biggest driver on that. But, you know, I think there's also a sort of camp that sort of has felt like, well, that only works if you reach kind of a threshold pressure that sufficiently, you know, sort of in some ways, I tend to think conceptually as open up the fall, right? In essence, you know, compensate enough for the normal stress to be able to overcome that sort of frictional stress and get the fall to move. So I think there's probably kind of an interplay that, I mean, again, I'm speaking hypothetically at this point, but you know, I'm thinking about interplay, right? Where you sort of need some level of pressure to kind of buy in and get it to start to have an ability to move. And then, you know, perhaps even small fluctuations in the pressure gradient could then sort of drive the amount of seismicity after that point. So, you know, in essence, you got to buy in, and then at that point, it becomes more sensitive. Again, I would say that sort of working model comes from a variety of different work I've seen in the literature to try and sort of piece that together based on what we've seen observationally here, right? But for us, the sort of stark sort of observations, right, is when we've got these big peaks in the pressure gradient, we have very little seismicity in many of these places, right? And so it isn't until you kind of have that sustained higher pressure, you know, I mean, you know, it's not that the pressure comes back down, right? The gradient comes back down because you kind of are hit that plateau of the pressure. But after, you know, you've got a sort of year or so of that high pressure, that's when the seismicity starts to pick up. So again, you know, I could envision alternative models, right, where that sort of high pressure gradient is disturbing the system in some way that we just can't measure with the kind of seismicity that we have available to us. Maybe some of that is aseismic that's going on at that level, and that over time, you know, that turns to a more seismic driven system, right? So again, trying to create an alternate hypothesis there, because I don't think we know quite enough yet to be able to kind of put the whole model together.
Thanks for that.
Sure.
So I think Jason Ellison has a few other questions. Jason, do you want to unmute yourself and?
Sure. Yeah. First, great presentation. Very interesting to me. I'm actually working part-time for the KGS screening kind of on the eastern side of the central Kansas uplift as northern Oklahoma for C2 sequestration. And our partner, you know, is very interested in not screwing up their water injector wells when we inject CO2 into the area. So we've been looking at several of the intervals, but especially the Arbuckle as you know, kind of an ideal target. So I guess, you know, some of the comments, questions might be, you know, there is quite a difference in terms of injected volumes cumulative on the CKU versus what you've got in southern Kansas, northern Oklahoma. And KGS had done some modeling work for other projects, just looking at fault azimuth or structure azimuth relative to modern day stress fields. And it seemed to me like, you know, the ones on the CKU were oriented in such a way where they might be less likely to slip relative to the ones that are kind of more on that Nemaha Ridge strike. So that would be kind of, you know, observation or question perhaps number one is, you know, do you think that is a dominant driver on if these things are going to move at, we'll just say, relatively lower injection volumes because it feels to me a lot of things outside the CKU would be lower injection volume. But then the CKU is also very special in that it's been a bump for a long time. And because it was a bump for a long time, you get a lot of karst fracture systems developed in the Arbuckle that I think would be more open to, absorbing the water that you inject relative to some of the areas elsewhere. So, have you looked at, have you been able to look at, the injection rates relative to the kind of permeability system you've got? And it probably is you don't have that granularity of data, but those are just kind of two thoughts in my mind as one azimuth of fault domains, as well as the kind of rock fabric in the Arbuckle that you're injecting into. Any granularity there from your side?
That is a great idea, but like you said, don't have capability to look at those things, but that is a great consideration.
Yeah, Jason, I particularly like your idea about trying to think about the sort of fabric in the region to try and assess whether or not there's some anisotropy in the permeability, right? I think, a key question for us is, why is that region, Jewell County, off to the northeast, the area that's become active? Clearly it's being driven by, just distant disposal, but, if the pressures are migrating in, that far away to the northeast, why are they not also migrating to the north or to the east, right? And so one possibility is that there is some anisotropic permeability of fabric that's driving the fluid pressures in that direction. The other possibility is that, you just have a fault system in that area that's more prone and susceptible to activity. Again, I could add a third possibility, right? Is just that there's more connection between the Arbuckle and the basement in terms of those through-going structures. You highlighted it in the CKU, right? There's clearly pathways for that there, given the nature of the fault system. We do wonder about Jewell County in that, are we just close enough to a fault system there that we've got more through-going permeability systems that allow for the fluid pressures in the Arbuckle to transmit down into the basement more efficiently there than in other places?
No, that's awesome. We should talk. I may be able to share some additional data with you guys that's more granular, but I can't commit to that because it's not my data.
Sure.
But there may be a little bit more I could show and tell about that, provided that all the powers that be sign off on it. But great stuff. Really timely work.
Awesome.
Yeah, I saw you mentioned in your one of the questions, Jason, that you said that there is some class 1 on the CKU. Do you know how far north those are, or an estimate of latitude?
I probably shouldn't say right now.
Oh no,
I'll just say they're on the CKU.
Yeah, fair enough.
Yeah.
Fair enough.
No, I was just, no, I understand, but that was interesting because I didn't realize, or I guess from what I saw on the KGS website of class 1 wells, that I didn't think they extended that far, but yes, we should talk later.
So ARMA is all about collaboration in the community. So great to see we're connecting potential collaborators here. So Zach Liu has an interesting question. Zach, I see you're still online. Do you want to unmute yourself? Maybe I'll ask it for him. It ties into the same sort of discussion, I guess, the structure piece and the lack of seismicity between the injection and the site. Any comments there?
Yeah, I mean, it's similar to the hypotheses I've tossed out here, right? That it's a bit more deliberate in that sense, right? That if we're going to get the fluid pressures up to Jewell County, it has to traverse that area in between, right? So you clearly have to have fluid pressures at least as large as are in Jewell County in between the CKU and Jewell County, right? So that's probably more definitive, right? Even if there's an anisotropic network that kind of allows fluid pressures to migrate in that direction, you certainly would have to have it there. The lack of seismicity then in between does, cause us to sort of consider, is it that the faults in that area are not as optimally oriented, that they're not as close to failure, that they're not as plumbed as well, that there isn't sort of through-going structures that communicate those fluid pressures from the Arbuckle to the basement. I think any one of those things are a possibility. But yeah, as Shannon noted, not a lot of 3D seismic available to us to be able to try and assess some of those things. But again, I think that's, forward looking, right? Though we now have some testable hypotheses to try and match up with the structure in some of these areas to try and explore, can we start to rule out some of those hypotheses?
Great. And I see Margaret Glasgow's online and has a question. Margaret, do you want to unmute yourself?
Sure. Hi, Mike and Shannon. That was really cool to see. And I think it's really interesting seeing the seismicity sort of moving further out and almost into another state. And I think that's one of the interesting things from a lot of these places where there's been a lot of injection and now we're actually seeing like what happens 20 years later. So yeah, I was just kind of curious. I'm always kind of trying to think of like, how can we match things to what we're modeling just to try to see like where's the seismicity headed. So I was just wondering if you had estimated any sort of like diffusion rate specifically from those two wells that were, I guess, 50 kilometers away, and then the seismicity moved towards the northeast. And if that makes sense with, something that people use in modeling.
Yeah. So I don't think we're going to have a good answer for your question, but I'll give you some reasons why, and then I'll still make some guesses anyway. But yeah, the issue is that, it seems as though that Jewell County seismicity is being driven by the Central Kansas uplift injection, and that injection has been going on at high rates for a long period of time, right? So, the high rates go back even prior to 2000, right? And so to try and deduce a diffusion rate is tough when you don't have these peaks in the injection, right? So I think that's what really kind of hampers our ability to estimate, what that diffusion rate is. That said, again, I think we have some, information from Oklahoma, right? That, some of the models that have been put together for Oklahoma using, estimates of the Arbuckle would suggest pretty high, diffusivities, above 1. And so, again, I would imply that those things should be relevant in Kansas too. I don't think the Arbuckle's that different in northern Kansas to imply that we should be looking at substantially different diffusivities there. I also tried to tie a little bit to West Texas. Some of the estimates for diffusivity are on the order of like 20 out in the Culberson County area in West Texas. And that's based on much better pressure measurements downhole. So again, we can't just take those measurements and directly, insert them into Kansas, but I'm just trying to get a feel for the order of magnitude of diffusivity that people are looking at right now. And it's not small. So that's sort of where I would be looking at, trying to use some relatively high diffusivities to see, do they match the patterns that we observe? It's a little tougher in those northern areas because we don't have downhole pressure measurements to directly tie to.
Cool, thank you.
No worries. I saw another question in the chat from the Integrity in situ folks about the flack from operators from the public or stakeholders. Shannon, I'll let you weigh in on this one, but my impression has been generally no. These events have generally been flying somewhat under the radar. I mean, we see, again, most of what we can see is sort of news reports, right? And so when these fours happen, they hit the news, but then die out pretty quickly. There does not seem to be this groundswell of concern over this at the sort of public level, at least that we've been able to track. Shannon, if you've heard differently, chime in. But
that's
exactly
exactly
my impression.
what I've heard is that again, that's why what interests me so much in this project is that I saw these were all going on. I was like, why has no one mentioned these? Why aren't a bigger deal? Like similar size magnitudes in other states, but yeah, it's like they've been going under the radar. So that's why what drove this project was exactly that.
Why aren't people paying more attention, right?
Yeah, the focus is in southern Kansas, and if there's similar magnitudes further north, I'm like, why? What's the difference between? Yes, there's a lot more in southern Kansas, but they've been injecting just as much, but just hasn't been as big of a change as you saw in the south near the border.
Yeah, Madi, I see your comment here now. Also, a good reminder about northern central Texas also having pretty good evidence that you need disposal from tens of kilometers away in order to sort of best explain the seismicity. I'd forgotten about that, but you're right. The Venus case is a pretty good one as something to point to. That was a puzzle for quite a bit of time, I think, as to how could you explain that Venus area seismicity. But yeah, when you allow disposal from more distal wells to contribute, it becomes a little bit easier to explain.
Yeah, exactly. We did modeling for this purpose. We considered the small models versus big models in the orders of tens of kilometers, ultimately for the biggest model. And we were able to explain that cluster of earthquakes in Venus using that big model. So that when you were talking about the relation between saltwater disposal and a specific cluster and the distances within 40-50 kilometers, it reminded me of these cases that we considered. Yeah, pretty interesting.
Yeah. I mean, obviously, Shannon and I are pretty keen to do some more fluid pressure modeling on this work. Neither of us has had enough time to do it. It's probably the simplest way to explain it. If folks are interested to pursue it, please reach out.
Any chance that from your template matching catalogs, you can extend that to add more focal mechanisms?
So it's a good question, not one that I had considered, but I saw that Rob Scomo just put out his code for doing focal mechanism estimation, using a limited set of sort of observations that he's been working on in the inference mechanism sort of estimation strategy. So I would say I'm more keen to do it now that Rob's got that code out and available for folks. I would say, Jens, I think Shannon and I have both been interested to kind of explore the template match catalog, both in terms of trying to better assess the fault orientations as well as the focal mechanisms. But again, it's just been a limited time issue. But yeah, I mean, helpful to know that it would be important to kind of assess a bit more what's going on.
Yeah, because the SOU catalog is enticing, but there's just not enough mechanisms there to do an inversion that's reliable. So you just see what must be happening, but you can't say a whole lot more than that. Or at least I can't.
Yeah, Jens, what would you say is kind of that threshold for success with the focal mechanism inversions?
You need at least, I think it's 20 mechanisms in an area with a roughly uniform stress field, but that's the bare minimum. Ideally you'd be going with 35 or something like that.
Okay. Yeah, it gives us something to shoot for.
Yeah.
Appreciate it. Yeah, I mean, as you saw, right, there's clearly some variation amongst these different regions, right? But yeah, with a limited number in each of these regions, it's a little hard to kind of deduce what's the primary driver on it.
Mm-hmm.
Could I ask a question real quick? I may have missed this, but given Jens's stress map, do those normal faults make sense up in the northern part of Kansas, or I just can't remember what the map looks like, and Jens is here and y'all are here. So.
Shannon, if I remember right, when we looked, it didn't appear that we'd be getting the normal faults in that part of Kansas yet. Do I remember that right?
I thought so, but Jens could chime in.
He probably knows the map better than we do.
Yeah, well, I'm looking at the map now. It's teal on the map. It's normal and strikes at faulting. So I'm not surprised to see normal faulting there. What I am surprised by is the orientation of the p-axes or the t-axes there, because it suggests a SH max orientation that's closer to northwest southeast than the closer the east-west that you see over down in Oklahoma. So I'm more surprised that there appears to be a rotation SH max orientation, but we don't have enough information to nail that down as a proper stress measurement.
Yeah, I appreciate you brought that up, Margaret, because I mean that is something Shannon and I had noticed, is it didn't quite fit with what we had seen in the map, but yeah, I mean I think it's really just the map that was constructed had limited set of observations to sort of tie through that sort of northern Kansas area and into Nebraska, given how limited seismicity there was. Yeah, I think, given there's been more seismicity recently, there's probably an opportunity with a little bit extra work to try and pull out enough stress measurements to be able to do a better job at it with another go around.
And we'll be updating the stress map at some point here, and that those focal mechanisms, even the individual ones, will go into defining AFI more there. And probably it'll be, I'm guessing, just looking at this, it'll be a slightly bluer color than is on the map.
For sure.
I wouldn't be surprised if there's some strike slip faulting too, because not far away there is strike slip faulting active.
Yeah, we did note in this CKU area, right, that there are some of these oblique faults, focal mechanisms, right, that they tend to be a little bit more straight strike slip in Hutchinson and Salina, but that they tend to rotate a bit more in the CKU area. Again, limited number of observations to make that inference, but as you noted, right, if we had 20 or so in each of these regions, that would make it a little bit easier to see, is it dominant or is there a mixture?
Yep.
Hey, sorry about that, guys. I got a call, so and actually I'm gonna have to bail, but thanks again, Mike, and thanks, Shannon, even though like we joked about, at least at the end and the most important part, the Q&A.
Sure, absolutely.
No, this has been great feedback so far, so glad Mike was able to present.
Yep.
Good. All right, well, thanks everybody, and Marty, hopefully you got a chance to ask your question in relationship to your publication.
Yeah, we did. We got a chance to cover it.
Yeah, we covered it. Thank you so much. It was a great webinar. Thank you, Shannon. Thank you, Mike.
Yeah, thank you all
Yeah,
to
absolutely.
help with our paper.
Yeah, no worries. Yeah, as we said, we were holding off until after getting some feedback today, but it's been great.
Talk to you later.
Thank
All
you.
right, see y'all.
Have a great weekend. Bye-bye.